gutter is not typically considered part of equipment that requires workspace. According to the National Electrical Code, workspace is defined as that space around electrical equipment that is necessary for examination, adjustment, servicing, or maintenance of the equipment. Gutters are not electrical equipment and do not require workspace for servicing or maintenance. Whether or not AC people can place a unit under a gutter depends on several factors. Firstly, local building codes. Secondly, servicing and maintenance requirements. And thirdly, airflow. Local building codes may restrict the placement of AC units under gutters. AC units require space for servicing and maintenance. If the gutter is too close to the unit, it may be difficult or impossible to access the unit. AC units need adequate airflow to operate properly. If the gutter is blocking the airflow, the unit may not function efficiently. In general, it is not recommended to place an AC unit directly under a gutter. However, if there is no other viable location, it may be possible to install the unit under the gutter if the following conditions are met. Firstly, the local building code allows it. Secondly, there is sufficient space for servicing and maintenance. Thirdly, the airflow is not obstructed. It is important to consult with a qualified electrician or HVAC technician before installing an AC unit under a gutter to ensure that it is done correctly and safely. The location of the trough is not relevant to the question of whether or not AC people can place a unit under the gutter. When dealing with electrical installations and equipment placement, it's essential to adhere to the National Electrical Code and any local building regulations to ensure safety and compliance. The NEC provides specific guidelines regarding workspace requirements around electrical equipment. These workspaces are designed to allow qualified personnel to safely examine, adjust, service, or maintain electrical equipment. The dimensions of the required workspace depend on the voltage of the equipment and the presence of any exposed live parts. It's crucial to maintain these clearances to prevent electrical shock hazards and ensure that maintenance can be performed safely. Remember that gutters themselves are not considered electrical equipment. They are structural components designed to channel rainwater away from a building's foundation. Therefore, they do not fall under the NEC workspace requirements. However, their presence can still affect the placement and accessibility of nearby electrical equipment. When installing an air conditioning unit near a gutter, several factors must be considered. Firstly, check local building codes and ordinances. These regulations often specify minimum clearances between equipment and building features like gutters. They may also have specific requirements for the placement of AC units to minimize noise and visual impact on the neighborhood. Secondly, ensure adequate space for servicing and maintenance. AC units require periodic maintenance, including filter changes, coil cleaning, and component inspections. The presence of a gutter directly above or adjacent to the unit can obstruct access to these components, making it difficult to perform necessary maintenance tasks. It's essential to provide sufficient clearance around the unit to allow technicians to work safely and efficiently. Thirdly, consider the impact on airflow. AC units rely on proper airflow to dissipate heat and maintain efficient operation. If a gutter is positioned in a way that restricts airflow to the unit's condenser coil, it can reduce its cooling capacity and increase energy consumption. Ensure that the AC unit has unrestricted access to fresh air to prevent overheating and ensure optimal performance. In some cases, it may be necessary to relocate the gutter or modify its design to accommodate the AC unit. This may involve installing a shorter section of gutter, diverting the downspout, or adding a splash block to prevent water from splashing onto the unit. Consult with a qualified contractor to determine the best solution for your specific situation. If you're unsure about the applicable codes or best practices, it's always wise to consult with a qualified electrician or HVAC technician. These professionals have the knowledge and experience to ensure that your AC unit is installed safely, efficiently, and in compliance with all applicable regulations. They can also provide valuable advice on how to maintain your unit to ensure its longevity and optimal performance. When planning the placement of an AC unit, it's crucial to consider the unit's dimensions and operating requirements. AC units come in various sizes and configurations, so it's important to choose a unit that is appropriate for the size and layout of your home or building. A unit that is too small will struggle to cool the space effectively, while a unit that is too large may cycle on and off frequently, leading to energy waste and premature wear. The unit's operating requirements include its electrical needs such as voltage and amperage. Ensure that your electrical system can handle the unit's power demands and that you have a dedicated circuit breaker for the unit. It's also important to provide adequate grounding to protect against electrical shock hazard. In addition to the technical considerations, there are also aesthetic factors to consider when placing an AC unit. Choose a location that is visually appealing and minimizes the unit's impact on the surrounding landscape. Consider screening the unit with landscaping or fencing to hide it from view. You can also paint the unit to match the color of your house or building. Remember that the goal is to integrate the AC unit seamlessly into your property while maintaining its functionality and accessibility. Before installing an AC unit, it's essential to obtain any necessary permits from your local building department. Permit requirements vary depending on the location and the scope of the project. Failure to obtain the proper permits can result in fines, delays, and even the removal of the unit. Contact your local building department to inquire about the permit requirements in your area. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations in the United States. It is a widely adopted standard that aims to ensure the safety and reliability of electrical systems. The NEC is updated every 3 years to reflect the latest technological advancements and safety practices. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a law itself, but it is often adopted by state and local governments as part of their building codes. Compliance with the NEC is essential to ensure that electrical installations are safe and meet industry standards. Article 100 of the NEC provides definitions for various terms used throughout the code. These definitions are important for understanding the intent and application of the NEC requirements. Article 110 covers general requirements for electrical installations, including workspace, guarding, and identification of equipment. Article 210 covers branch circuits, which are the circuits that supply power to outlets, lighting fixtures, and other electrical devices. Article 220 covers load calculations, which are used to determine the size of the electrical service and branch circuits required for a building. Article 250 covers grounding and bonding, which are essential for preventing electrical shock hazards. Article 300 covers wiring methods, which specify the types of wiring that are permitted for different applications. Article 310 covers conductors for general wiring, including their ampacity and insulation requirements. Article 400 covers flexible cords and cables, which are used for connecting portable appliances and equipment. Article 430 covers motors, motor circuits, and controllers, which are used in a wide range of industrial and commercial applications. Article 440 covers air conditioning and refrigerating equipment, including installation and safety requirements. Article 500 through 516 covers hazardous locations, which are areas where flammable gases, vapors, or dust may be present. These articles provide special requirements for electrical equipment and installations in these locations. The NEC is a complex and comprehensive document, so it's essential to have a thorough understanding of its requirements before undertaking any electrical work. Consult with a qualified electrician or electrical engineer if you have any questions or concerns. When working with electricity, always follow safe work practices to prevent electrical shock and other hazards. Wear appropriate personal protective equipment, such as safety glasses and gloves. De-energize circuits before working on them, and use lockout/tagout procedures to prevent accidental re-energization. Test circuits to verify that they are de-energized before starting work. Never work alone on electrical equipment, and always have someone nearby who can assist you in case of an emergency. Consider some key electrical concepts. Voltage is the electrical potential difference between 2 points in a circuit. It is measured in volts. Amperage is the measure of electrical current flowing through a circuit. It is measured in amps. Resistance is the opposition to the flow of electrical current in a circuit. It is measured in ohms. Power is the rate at which electrical energy is used in a circuit. It is measured in watts. Ohm's law states the relationship between voltage, current, and resistance in a circuit. It is expressed as volts equals amps times ohms. Understanding Ohm's law is essential for troubleshooting electrical problems and designing electrical circuits. Series circuits are circuits in which components are connected in a single path, so the same current flows through each component. Parallel circuits are circuits in which components are connected in multiple paths, so the voltage is the same across each component. Series parallel circuits are circuits that combine both series and parallel connections. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault current to flow, by protecting against electrical shock hazards. Bonding is the process of connecting metal parts of electrical equipment together to create a low impedance path for fault current to flow. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. Circuit breakers are reusable devices that trip open when an overcurrent occurs, while fuses are one-time devices that melt and open the circuit when an overcurrent occurs. GFCI, or ground fault circuit interrupters, are devices that detect ground faults and quickly interrupt the circuit to prevent electrical shock hazards. SIs, or arc fault circuit interrupters, are devices that detect arc faults, which are dangerous electrical conditions that can cause fires. Surge protectors are devices that protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage electronic components. Uninterruptible power supplies, or UPSs, are devices that provide backup power to electrical equipment in the event of a power outage. Electrical boxes are enclosures used to protect electrical connections and devices. Conduit is tubing used to protect electrical wiring from damage. Wiring connectors are used to connect wires together safely and securely. Electrical tape is used to insulate electrical connections. Wire strippers are used to remove insulation from wires without damaging the conductors. Multimeters are instruments used to measure voltage, current, and resistance in electrical circuits. Clamp meters are instruments used to measure current without interrupting the circuit. Voltage testers are instruments used to detect the presence of voltage in electrical circuits. Cable testers are instruments used to test the continuity and integrity of electrical cables. Ground resistance testers are instruments used to measure the resistance of the grounding system. Insulation resistance testers are instruments used to measure the resistance of the insulation on electrical wires. Power quality analyzers are instruments used to measure and analyze the quality of electrical power. Thermal imagers are instruments used to detect hot spots in electrical equipment, which can indicate potential problems. When working with electrical equipment, always follow the manufacturer's instructions and safety guidelines. Inspect equipment for damage before use, and replace any damaged equipment immediately. Use the right tools for the job, and use them properly. Keep your work area clean and organized to prevent accidents. Never work on electrical equipment while you are tired or distracted. Be aware of your surroundings and watch out for potential hazards. If you are unsure about anything, ask for help from a qualified electrician or electrical engineer. When working with electrical panels, always wear safety glasses and gloves. Use a voltage tester to verify that the panel is de-energized before opening it. Inspect the panel for signs of damage, such as corrosion or arcing. Tighten all connections to ensure that they are secure. Label all circuits clearly and accurately. Keep the panel clean and free of debris. Do not overload circuits and use the correct size circuit breakers or fuses. Never bypass or disable safety devices. If you encounter any problems, such as tripped circuit breakers or flickering lights, investigate the cause and correct the problem before restoring power. If you are not qualified to perform electrical work, contact a qualified electrician to do the work for you. Remember that electrical safety is everyone's responsibility. By following safe work practices and using the right tools and equipment, you can prevent electrical shock and other hazards.